Hello, Dr. Garimala. My name is Vinay Murthy, and this is the video for the first assignment of data mining class. Now I'm going to be shifting to the screen. So I've decided to work on the bike bias dataset. This dataset consists of different features, and the value which we'll be predicting is whether a particular person is going to buy a bike or not, depending on different features which have been specified here. That is marital status, gender. I've changed the numeric categorical data into numeric data. As you can see, income data is the only continuous variable, whereas all the others are pretty much categorical, and I've changed it into dummy, most of them into dummy variables. Like commute distance, I've changed 0 to 1 mile to 1, and different for different, like 2 is 2 to 3 miles, etc. So the best part about this is about using Azure ML Studio is it provides basic descriptive statistics while we are looking at the data set itself. Like if we just click on income, we get to know the basic descriptive statistics like the average salary, the median salary. It would be a better judge of salary and income, and we can compare it to different features as well to understand the relationship and correlation between the features. Well, the next thing what I've done is I've again taken to summarize the data to better get a feel of the data. So I'll be showing the same. So this also provides pretty much the basic statistics, but a bit more than that. And there are other features under this particular operation, like sample skewness, sample kurtosis it provides, and as we can see clearly in the income range, the values are pretty high compared to other values in other features. So what we can do is we can scale the data such that a particular model what we are using would be able to better understand the features, the relationship between the feature and the predicted variable. So I've normalized the data. I've normalized only the income column, and I've used the natural logarithmic transformations, and again I've summarized the data after the normalization. So we can see here that income over here, as we saw, was pretty high. Even the mean was pretty high, and the sample skewness and kurtosis has come down now compared to the previous one, and all the other values have come down, pretty much scaled to the values in the other features. So after this, what I've done is so the best part about this is this summarization helps us better understand the data set, what we're dealing with, the correlations as I told before, and also it helps us make some basic assumptions about the data set to better understand and fit our model better and get a better function approximation. Then what I've done is I've split the data into two. One is for training purpose and another is for testing purpose to check whether our data is resulting in overfitting or no. The model which I've chosen is two-class decision forest, and as I told, I've split the data and I've taken 80%. I've taken 80% of the data for training and 20% for testing. So this is our trained model I would like to show, and as I've chosen 8 decision trees, sample decision trees to be 8. That is over here. I'll be showing. Well, meanwhile, so it's finished loading now. So it's provided a basic decision tree of our predictions and different nodes on which the prediction has been made. And how the nodes have been chosen is one of the ways we can do that for decision tree algorithm would be to use ID3 algorithm, where it we calculate the entropy values, and the nodes with the lowest entropy value is chosen, and they're again further split into different, based on different features they have. Like say for example, we take this particular prediction, that is a zero prediction. That means they're not going to buy a bike. On what basis? So the commuting distance is 5 to 10 miles. Cars, they have one car. Marital status, not married. Marital status, actually married, not married. Education numeric is bachelor's. Children is, they have 3 children. Income is pretty low. So the prediction made is the person is not gonna buy a bike. Makes pretty good sense, because if I was in the case, like if someone had one car and 3 children, and the income rate is so less, pretty much wouldn't go for another bike or another vehicle. Because, and I think the major influencer here would be income itself. Let's check for another prediction. Let's check for a prediction where they do buy a bike. Yeah, let's check this one. This says commuter distance is 4, 0 children. Cars they have 3 cars, and income is 0.739. That's way bigger than what we checked before. So this person will go ahead and buy a bike. So you can see that there's a good strong relationship between income and our predicted variable. Next thing I want to show is the score of the data model after this. And in the score data model, in this, the main criteria for us would be to see the scored labels, that's the predicted labels, versus the actual. So 1, 0, it's predicted 0, and these are scored probabilities, which tell us like, and again, just clicking on that would give a basic statistics of things. Scored probabilities would give like what is the probability of our model to be saying it's 0 when it's actually 0. That's 12.5% for this particular label, depending on different features over here, like 66 age, cars have 2. So the prediction would be 0, 0, and 12 out of 12.5% is the probability for that prediction. And the next thing I want to show is what train model. Sorry, I've chosen the column only purchase bike numeric, because that's what we're going to be training our model on, to predict whether a person has bought a bike or no. And evaluation model, I would like to visualize the results for evaluation model as well. So this provides like an ROC curve between true positive and false positive rates, and so in this curve itself we can determine our model is doing pretty fine, not that bad. It's tilting slightly towards the false positive rate, but still has a good projection of true positive as well here. This would be a good estimate of our of the accuracy of our model, that is true positive and false negatives. Of all the true positive, how many actually has the model predicted to be true, that is 65, and of all the positive, how much have they predicted as negative, that is the false negatives, and the accuracy for that is 62.5, and these are the same. How many so the ratio of these both would basically give us the misclassification rate, that is the accuracy of a particular model. And these are different bins where we can find different accuracies, like 0 to 1, how many of our data points are there, what are the scores and scored probabilities, that scored labels, and what is the accuracy of those labels which we have been predicted. And it also provides F1 score, which is nothing but a harmonic mean between precision and recovery. One more important thing is the threshold is mentioned to be 0.5. That says that the whole data, the whole model is predicting for whomever the probability of buying is more than 0.5 would be predicted they will buy. That will be classified as 1, and less than 0.5 would be classified as 0. This is about it, and there are way more as I told, way more options here, like statistical from summarized data, testing hypothesis, and even we have anomaly detection for principal component analysis to find out different hidden features. Really a good tool, I would say, and good tool suggested. Thank you for that, Professor. And that's about it for this particular assignment. Thank you for listening.